There are over 400 billion stars in the Milky Way. And yet, when scientists sit down and ask themselves where they should look for life, they keep coming back to the same address. 40 light-years from Earth, a cold, faint star sits quietly in the constellation Aquarius, so dim it cannot be seen without a telescope. Its name is Trappist 1, and around it orbit 7 rocky worlds, each roughly the size of our own planet, each silently waiting to be understood. For years, that number 7 felt almost cruel. 7 planets, all circling a star too faint, too violent, too strange to offer easy hope. One by one, scientists have eliminated most of them. Too close to the star, too much radiation, no sign of an atmosphere, no chance. But in science, as in life, it only takes one. And right now, one world keeps defying dismissal. One planet refuses to be ruled out. Its name is Trappist 1e, and the James Webb Space Telescope may have just glimpsed something extraordinary around it. What we are starting to understand about this world is unlike anything seen before in the search for life beyond our solar system. You are watching today in the space world. Today, we are traveling 40 light-years to investigate the most compelling case for habitability ever assembled around a distant star. We will break down the new James Webb data, examine what Trappist 1e's atmosphere might look like, and ask the question that keeps planetary scientists awake at night. Could something be alive there right now? Trappist 1 is not the kind of star that commands attention. It is classified as an M8 red dwarf, sitting at the very bottom of the stellar hierarchy. Its mass is so small that it barely qualifies as a star rather than a failed one. It produces roughly 1,800 times less energy than our Sun, a difference so vast it is difficult to visualize. If our Sun were a bonfire capable of lighting a stadium, Trappist 1 would be a single candle, lit in the corner of an empty room. It was first identified in 1999, but remained unremarkable for years. That changed dramatically in 2017, when the Trappist telescope network, split between the mountains of Chile and Morocco, confirmed something astonishing. Transit photometry, a method that monitors the regular dimming of a star as orbiting planets pass in front of it, revealed not 1, not 2, but 7 planets circling this otherwise forgettable star. Every single one of them is rocky. Every single one of them is broadly Earth-sized. In the entire history of exoplanet science, no other star system has produced a lineup remotely like it. What makes red dwarfs strange hunting grounds for life is precisely their nature. Because they emit so little energy, any planet warm enough for liquid water must orbit extraordinarily close to the star. We are talking about distances so small, they would fit comfortably inside the orbit of Mercury around our own Sun. At those distances, a planet does not simply orbit its star, it gets locked to it, one face baked forever in permanent daylight, the other sealed in a darkness so total and so cold that no sun has ever risen there. This is the condition scientists call tidal locking, and it is one of the central dramas of Trappist 1e's story. Of the 7 Trappist 1 planets, Trappist 1e sits in a position that has earned it more scientific attention than all the others combined. It orbits at about 1/13 the distance of Mercury from our Sun, completing a full year in just over 6 Earth days. And yet, because Trappist 1 is so much cooler and dimmer than our Sun, that distance places 1e squarely within what astronomers call the habitable zone, the orbital band where temperatures could theoretically allow liquid water to persist on a rocky surface. The planet itself is around 9/10 the size of Earth. That matters more than it might seem. A planet too large builds up crushing atmospheric pressures. A planet too small struggles to hold an atmosphere at all. Trappist 1e sits comfortably in the range where a nitrogen-oxygen atmosphere, something like our own, is physically plausible. It receives around 2/3 of the solar energy that Earth does from our Sun. Not identical conditions, but close enough that the comparison is hard to dismiss. One by one, its neighbors have been eliminated from serious consideration. Trappist 1, B and C are scorched, Venus-like worlds too close to the star. Trappist 1, D sits right at the inner edge of the habitable zone, likely too warm. Trappist 1, F, G and H are almost certainly too cold. sitting at distances where any water would likely be permanently frozen. But TRAPPIST-1e keeps surviving every filter scientists apply to it. It remains, after years of scrutiny, the most likely candidate for habitability that humanity has ever identified outside our own solar system. Looking for an atmosphere around a planet 40 light-years away is not a task that should be possible. And yet, the James Webb Space Telescope was built, in part, to do exactly this. Its instrument suite is calibrated to sensitivities that no previous observatory could approach, and TRAPPIST-1, counterintuitively, happens to be an ideal target for it. The technique Webb uses is called transmission spectroscopy. When a planet passes across the face of its star, starlight filters through the outermost edges of the planet's atmosphere before reaching Webb's detectors. Different gas molecules absorb different wavelengths of that infrared light. Carbon dioxide leaves a distinctive fingerprint. Methane leaves another. Water vapor, nitrogen compounds, oxygen. Each one pulls specific wavelengths out of the spectrum, like a signature drawn in light. By comparing the star's spectrum during a transit against its spectrum outside of one, scientists can reconstruct what gases are present in the atmosphere filtering that light. What makes TRAPPIST-1 especially useful for this technique is the very thing that makes it seem so unlikely as a host star. Because the star is so dim, a planet passing in front of it blocks a proportionally larger share of its total light output than the same planet would block from a brighter star. That larger relative signal is far easier to measure with precision. The data Webb has collected from the TRAPPIST-1 system is, by some estimates, 10 times more detailed than anything gathered on any comparable exoplanet target. A team known as the DREAMS Collaboration, which stands for Deep Reconnaissance of Exoplanet Atmospheres through Multi-Instrument Spectroscopy, committed their guaranteed Webb observation time to this system the moment the telescope became operational. So far, they have observed 4 transits of TRAPPIST-1e. What those transits revealed has reshaped the conversation entirely. The first thing the data did was close doors. A primordial atmosphere, the light hydrogen and helium envelope a planet is born with, shows no sign of existence around TRAPPIST-1e. Radiation from the star during its early, more violent phase almost certainly stripped that layer away long ago. A thick carbon dioxide atmosphere like Venus sits in the range where Webb would detect it clearly. It does not appear to be there either. A thin Martian-style atmosphere of sparse gas also does not match the spectral readings produced by the 4 transits observed so far. That process of elimination might sound discouraging. It is not. Each of those atmospheric types would render the planet uninhabitable by any biology we understand. Ruling them out is progress. What the data does not rule out is more significant. The spectral readings are consistent with a heavier secondary atmosphere, the kind a geologically active rocky planet can generate over billions of years through volcanic outgassing. Nitrogen, carbon dioxide in moderate concentrations, water vapor, methane. These are all physically plausible under the current data. A surface pressure near one atmosphere, close to what you are breathing right now, cannot be excluded. And a planet with that kind of atmospheric mass, combined with its tidally locked geometry, might still sustain liquid water across much of its surface through atmospheric heat redistribution from dayside to nightside. Were that picture confirmed, it would represent the most consequential discovery in the history of science. The data currently leans, though modestly, toward a cooler and drier picture. The planet may not host a global ocean, but the science has not closed that door either. The team has more transits planned, with 15 additional observations scheduled over the coming months. What they are specifically trying to detect is a carbon dioxide signature, which would confirm the presence of a proper secondary atmosphere and fundamentally change what we think is possible around stars like TRAPPIST-1. Before hope settles too comfortably, there is a force in the TRAPPIST-1 system that has no equivalent in our own neighborhood: the star's fury. Close your eyes for a moment and imagine standing on the surface of TRAPPIST-1e. The star above you would appear more than 4 times the angular size of our sun in the sky. It would burn a deep amber red, painting the atmosphere in tones of perpetual dusk. Beautiful, almost. But watch carefully, because at any moment, a solar flare could arc off the star's surface with a violence our sun rarely matches. and Trappist-1 produces them constantly. The most powerful geomagnetic storm ever recorded on Earth, the 1859 Carrington event, was a once-in-a-century catastrophe. Trappist-1 is estimated to produce comparable events multiple times per week. Each of those flares carries charged particles and ultraviolet radiation outward with tremendous energy. Over geological timescales, that bombardment is capable of peeling an atmosphere away layer by layer, particularly in the absence of a strong planetary magnetic field to deflect it. This is the central threat to Trappist-1E's habitability, and it operates on two timescales simultaneously. The first is the early phase. Red dwarf stars spend far longer than sun-like stars in their turbulent, flare-heavy youth. That is simply a consequence of their extraordinary lifespan. Trappist is expected to burn for another 10 trillion years, roughly 700 times the current age of the universe. The formative phase of such a star is proportionally extended, meaning Trappist-1e endured an intense stellar bombardment for far longer than Earth did during the equivalent period of our Sun's life. Any atmosphere building up through volcanic activity during that window would have faced relentless erosion. Whether enough survived to establish a stable envelope of gas around the planet is a question the data is still trying to answer. There is, however, a compelling twist. Some of that early ultraviolet radiation may not have been purely destructive. Laboratory experiments and theoretical models suggest that high-energy UV light can catalyze the formation of RNA precursor molecules, the chemical building blocks at the root of all known life. Life on Earth may itself have needed the violence of a young, active sun to get started. Trappist-1, for all its aggression, may have inadvertently provided the same conditions. Here is where the story of Trappist-1e becomes genuinely surprising. A planetary atmosphere needs more than just the right chemicals. It needs the planet beneath it to be active, pumping volcanic gases into the air to replenish what radiation strips away. On Earth, that volcanism is powered in part by the decay of radioactive elements deep in the mantle and by the residual heat left over from the planet's formation. Trappist-1e likely has both of those internal heat sources too, but it may have a third one that Earth entirely lacks. Because Trappist-1e is so close to its star and its orbit is not perfectly circular, the star's gravity squeezes and releases the planet repeatedly as it moves through each orbit. That stretching and compressing generates friction in the planet's interior, a process called tidal heating. Scientists have calculated that this could add as much as 0.18 watts of heat per square meter to the planet's interior energy budget. That is roughly 24 times the tidal heating flux that Earth receives from the Moon's gravitational pull, and the Moon's pull already contributes meaningfully to Earth's geological activity. We see a more extreme version of this process play out in Io, one of Jupiter's moons, which is the most volcanically active body in the entire solar system precisely because of tidal squeezing from Jupiter and its neighboring moons. For Trappist-1e, that tidal heating could mean a persistently active mantle, ongoing volcanic resupply of atmospheric gases, and a hot enough interior to sustain the kind of convecting molten iron core that generates a magnetic field. A global magnetic field does not just make for dramatic auroras. It is the primary shield between a planet's atmosphere and stellar radiation. Earth's magnetic field has protected our biosphere for billions of years. If Trappist-1e has one of comparable strength, it changes the entire calculation around what that atmosphere can survive. The case for habitability around Trappist-1e therefore rests on a remarkable chain of interconnected mechanisms. Tidal heating keeping the interior active, volcanic activity sustaining the atmosphere, and a magnetic field preserving it against the star's outbursts. None of these things are confirmed, but none of them are ruled out, and every one of them is physically plausible based on what we already know about the planet. So where does this leave us? Trappist-1e may be a world with a nitrogen-rich atmosphere sitting at roughly Earth-like pressure, liquid water pooling somewhere on its surface, tidal heat stoking its interior, and a magnetic field holding its skies in place against a restless star. It may be alive, or it may be a cold, silent sphere of bare rock, stripped of every layer of gas it ever generated, sitting in the dark, with no atmosphere at all, and no prospect of ever having one again. Right now, the data does not force us to choose between those two pictures. It only tells us that the first one is still possible. And in the search for life beyond Earth, possibility is everything. The Habitable Worlds Observatory, a next-generation space telescope specifically designed to detect biosignatures around Earth-like planets, is currently targeted for a launch sometime around 2041. When it comes online, it may give us the definitive answer, but James Webb is not waiting. Its team has more transits to observe, more spectra to analyze, and a refined detection method built from everything the first 4 transits taught them. A carbon dioxide detection, if it comes, will confirm that a secondary atmosphere exists. That would not prove life is there, but it would prove the conditions for life are within reach. 40 light-years is close, in cosmic terms. The signal from Trappist 1E's atmosphere, if it is real, has been traveling toward us since before writing existed. And now, for the first time in the history of our species, we have a machine precise enough to read it. Whatever Trappist 1E turns out to be, the fact that we are asking this question at all, peering through 40 light-years of space at the atmospheric chemistry of a world around a candle-dim star, is extraordinary. The universe has given us 7 chances around one star alone. The idea that all 7 of them led nowhere feels, against all that scale and possibility, increasingly difficult to believe. If you want to stay up to date every time a discovery like this one comes through, you know where to find us. This is Today in the Space World. We will see you in the next one.